what we're doing today is continuing the stuff about the properties of logarithm. Right? Properties of logarithm. Okay. So basically, there are two main properties of log. Can anyone remind us what they are? Yeah, Caroline.
So log v xy equals log dx plus log dy.
Okay. So try to say it in English also. Like
Oh.
the log of a product turns into the sum of the logs of the factors. And the log of the product turns into the sum of the logs of the factors. And then next, another one. What's the other one?
So the log of a value raised to a power equals the power times the log of the value.
So log of something raised to a power turns into that power times the log of the thing. Okay. So right. So these are these great properties, and we were just starting to use them to do two things, which we call simplification and expansion. Maybe better than simplification would be called compression. Which is sort of like taking a bunch of terms and compressing them down into one term. And this is what was on your homework. But I think some people weren't here on Monday due to some reason or another. So let's do one more example of that. I guess you've already done it in your homework, but let's do another example. So here's one. Natural log of x squared minus 9 plus 2 natural logs of 1 over x plus 3 plus 4 natural log of x. Okay, and so this is sort of like a spread out thing, and we can use the properties of the log to make it a single term. Right? All of you have done this on the homework already, so maybe it's just a review. What do you do with this? What property do you use? Edison?
Multiply.
You multiply them, right? So this is a sum. Well, it's not really a sum of logs yet, because right now we've got a 2 here. Okay, we've got a multiple of a log here. So we can't
Square that one and then
right. Okay, so maybe the first thing we do is move this 2 in, so that we do get a sum of logs, right? Now we've got a natural log of 1 over 3 squared plus natural log of x to the 4, right? Right, we move these factors in, these multiplicative factors turn into exponents for the log, for the argument of the log, right? And now we have the sum of logs, and right, we know that the sum of logs turns into the log of the product, right? So now we've got a sum of logs, log of something plus log of something plus log of something, right? And it turns into the log of the product, right, which will be the log of the product. And so that's basically where we finished last time. Is that okay? Are people okay with that? It's nothing too tricky about it. You use there are two properties of the log, and you use them, how you feel like, to squish everything together. Okay. In the opposite direction, you can do the same thing. Right? You can expand. If somebody gave you this, you could expand it backwards using the properties in the opposite direction. Right? So, for example, if somebody gives you, say, log base 10 based on 29, cube root of 2x over 3x squared plus 1, right? Then we can take this apart apart, right, and break it down into, more simple term, into a sum, a combination of more simple terms. So how, I think this is pretty straightforward. I hope. What should we, actually, let me ask Rabia what might do. Right, we've got log of something, a cube root of something, right? This is something, the log of this thing to the 1/3 power, right?
So you take 1/3 log 10.
We can take the 1/3, we can pull the 1/3 out to the front first, same. Okay. And then what?
And then you can expand the 2x. So it would be 1/3 of log 10 2x minus log 10 3x squared.
Great, perfect. So you get 1/3 of log 10 2x minus the, what am I doing? 2x minus log of 3x squared. Right? Is everyone okay with the last step? I mean, you can either think of this as, one of the rules is that, if you take a log of a ratio, then it's the log of the top minus the log of the bottom, right? If you don't like to think that way, you can think of this as log. This thing here, we can rewrite as 2x times 3x squared plus 1 minus 1. Right? And then we've got a log of a product. Right? A log of a product. Right? This product, log of a product is the sum of the logs, right? So we get the sum of the logs. Right? And then we can pull the minus 1 out. Right? 1/3. Log 2x minus log 3x squared. Right? So you get the same thing. You can finish slightly longer than that. Okay, so that's, and you see what you get in the end, right? We get 1/3 of this log of something minus 1/3 of log of something, right? Right, we get some combination of logs. This is not in the text, but this is what's called a linear combination. A linear combination, where you have a bunch of things, and then you have like 5 of the first guy plus 7 of the second guy minus 6 of the third guy, something like that. That's called a linear combination. So the way that we would normally describe this is you're taking a linear combination of logs and then collapsing it down into one log. Or you're taking log of one term and you're expanding it out into a linear combination of logs. That's the vocabulary that makes it easier to talk about. Let's do one more. Okay. So log of, say, natural log of x squared root 2x minus 1 over 2x plus 1 to the 3/2. Okay. So take a minute or so and see if you can do it yourself. Or with and you can feel free to talk to other people and see if they got the same thing as you.
So you could do ln of the top six terms minus ln of the bottom six terms.
Okay.
And then the next step you can do for the first one, ln of x squared plus ln square root of 2x minus 1 minus everything else, but you could pull out the 3 halves in front. And then you can pull out the 2, put it in front of ln x, and then pull out 1 half, put it in front of ln 2x minus 1, and then minus 3 halves ln x.
Okay. And that's about it. Can't do much further. If you start doing more things, you're going to head backwards. So that's good. If you wanted to make it slightly, I mean, no, it's fine. There's not much one could do better. Okay, so you see how this works, right? Use the properties of logs, and the logs allow you to, those properties allow you to simplify or complicate it. You either end up with one term that's really complicated, or many terms, all of which are simple. Okay, sort of like you gain or lose either way. You don't end up with one term that's very simple, or many terms that are complicated. It's always like you end up with a simple expression, a single expression that's complicated, or many expressions, each of which is very, very simple. And this is actually useful. You'll see this trick. This will be used in calculus when you get to something called logarithm logarithmic differentiation. Okay. Let me try and give some idea of why we should believe these properties. Why is it true? Why are these properties true? Why are these properties true? Why is it true? Log of is the sum of the logs of factors. Log of something to the power is the power of multiplying. And that seems like maybe sort of mysterious. But the way you want to think is like this. Remember what log of y is, right? Log of y is the exponent, right? The unique exponent for which b to the whatever is 1. Right? It is the only exponent that has this property. It's the only number that has this property. Okay. So, when you think, so let's think about property 1. Log xy, right? What's log xy? It's the unique exponent. Let's say log base e, doesn't matter what the base is. It's the unique exponent a such that e to the a equals xy. So I'm just saying this again, okay? Right? Log of y is the exponent for which b to the something equals y. For example, log of xy is the unique exponent such that e to the something is xy. Okay? Now think, right? What's e to the log x plus log y? What's e to the log x plus log y? Well, by the properties of exponents, what is this? E to the something plus something is what? Well,
E to the xy. Or
um,
e to log xy.
well, let's just think like this. E to the m plus n. What's something to a sum of exponents? So
E to the m times e to the n.
e to the m, and e to the m times e to the n. Right? Well, what's e to the log base e of x? That's just x. What's e to log base e of y? Y. Right? So what do you see? We see that if you raise e to this power, you get xy. Right? Raising e to this gives you xy. But log xy is the unique power to which you raise e to get xy. Right? So this has got to be, so log x plus log y must be log xy. Right? There's only one power that you can raise e to get xy, and we call that thing log xy. Right? We call that thing log xy. Well, we notice that if we raise e to this power, the sum of the logs, we get xy. Well, then that thing must be log xy. Right? Because there's only one person who does this. Right? There's only one person with this ability. Right? You raise e to that thing, you get xy. Okay, so that's why log of xy is log x plus log y. Does that make sense? Does this argument make sense? Right? Who is log xy? Log xy is the guy that you take e to get xy. Okay. And then we think, what happens if we raise e to log x plus log y? We end up with xy. Oh, well then this guy must be log xy. Because there's only one person who does that. Make sense? Okay. This is a sort of simple argument, simple mathematical argument. You go on and the arguments become longer and longer and longer. In an upper level class, then the arguments I may go through one board and then start another board. And it usually doesn't take more than like 2 boards to get to an argument. But then, then you go to graduate school, and then your arguments get even longer. And you may have arguments that take hundreds of pages to do. And if they were spelled out in great detail, then they'd probably be thousands of pages. It's very interesting. So this is like the beginning. Okay, so let's see. So the other thing, so we've shown that this one, makes sense, right? This one, we understand why log of xy is this thing, because if we raise this thing, if we raise b to this, we get xy, right? Okay, so what do you think we're going to do with the second one? Right, to show that this is log of x to the y, what are we going to do? I'll say it again. Our first argument was there's only one number for which b raised to that number gives you xy. And we took b to the right-hand side and saw that we got xy. So this must be that number. How are we going to do the second one? Caroline?
Well, can't you do the same?
Do the same thing, right?
Say that there's only one unique solution for b to be something equals something.
Equals x to the y, yeah. So we take b to this and see what it is, right? So the same argument. 2 rated Caroline. Same argument. Maybe I should give you a point also on the next step. Same argument, right? Consider b to the y log bx. Right? What is it? Well, oh, wait a second. Because, so I was thinking, oh no, we're good. Okay, good. So we know that this is, say, b log b x. By the properties of exponents, right? What is b to the alpha beta? Well, that's b to the alpha to the beta, right? So we can write this thing as b to the log bx to the y. So,
It's probably a silly question, but could you also just write this e to the power y times log bx? Like, just switch the position of y and log x.
could we write this as b to the y
Yeah.
to the
It
log
would be the
bx?
same thing.
Sure.
Oh, okay, it would be the same thing. When solving it, okay.
But we'd run into trouble because we're trying to get to x to the y.
Oh, okay, no, that's what I wanted to know.
But it's true, we could go that way.
Okay.
Okay, well, it's b to the log x. X. So we get x to the y, yeah. Okay. Right. So, y log bx is the exponent, right, to which one raises b to get x to the y. Right? In other words, y log bx is log base b. Right? So, I mean, we were basically done at this point, but if you want to explain it a little bit more. Everyone know me? Same sort of argument, right? We take b to this thing, right? We say, oh look, we get xy. Well, that means that that's the exponent we raise b to get xy. In other words, it's log base b of x to the y. Let me show you why I paused and thought I was completely wrong. Here's what I was going to do first. I was going to say, well, look at this thing. This thing is b to the log base b x to the y. And so you get x to the y. Okay. Right? What's wrong with doing that?
Using the proof to prove the proof.
Yeah. That's right. So I'm using the fact that I'm trying to prove that fact. Right? We're trying to prove this fact, right? That you can pull the exponent out or put it in. Right? And say, okay, I pull this thing in. Well, how do I know I can do that? Right? How do I know I can do that? I'm trying to justify that fact right now. I can't do that. Right? Okay, so that would be completely logically a mistake. Right? To use the thing you're trying to prove. But fortunately, we don't have to. It's not the way we did it. It's not incorrect. Okay. So some sort of beginnings of mathematical argumentation or proof. Now I'm going to show you what is nearly useless. Changing the base of log. Okay. So here, let me show you an example. Suppose I have log base 2 defined, and I want to express log base 10. And I don't like log base 2 for some reason. I like log base 10. Okay. Okay. So what I do is I say, well, I'm going to let this thing called z. Whatever that thing is, I'm going to call it z. Well, this expression means that 2 to the z is 5. Like we switch the logarithmic expression for the exponential expression. Okay, and then I'm going to take log base 10 of both sides. So I get log base 10 of 2 to the z. I pull the z out. Log base 10 of 5. Okay, so that tells me that z is log base 10 of 5 over log base 10 of 2.
Z,
I divide both sides. I solve for z. So that, what was z? Z was log base 2 of 5, right? Log base 2 of 5 is log base 10 of 5 over log base 10 of 2. Carol?
Is that a universal law that if you want to put it in base 10 for logs, it'll always just be 10?
Yeah, so in,
Okay.
so in general, it is formula. Yeah, exactly. Like that log base a of x, you want to switch it to another base. Well, you can switch it to the other base, but you have to pay a cost. And that cost is that you have to divide by log base b of a, of your original base. Okay. So you see, it looks like you can almost just switch the base. Okay. You can, but you have to divide by this factor. Okay. And that's what we're seeing. That's what we're seeing here. And you see, Caroline, that 2 and 5 weren't really important.
Yeah.
Right? We could have written it like this: log base a of x, right? Let z be log base a of x, and then run through the same argument, and you would get the formula.
Okay.
Okay. I'm not going to give you another one. But good. Okay, but you know, this is not so important a trick, right? Moving from one log to another one.
Isn't it only important if you're actually computing it with the calculator? Because calculators don't do anything other than log base 10.
They only do log base 10?
Well, the base calculator I have only does log base 10.
Okay.
Usually.
I don't.
And
Must be.
no, you have to use the change of base if you want to actually compute it. On a, like, I don't know which one it is.
Okay.
The
so
basic
yeah.
sign.
Okay, so yeah, I guess in that case you would need.
Or not using calculators.
Right?
So,
That's true. So for us, it's sort of like an interesting fact. Okay, let me put up some common errors that the book lists. Common errors that people make dealing with the log. First, sometimes it happens that people think that the log of the sum is the sum of the logs. Okay. So, following are false. Are not true in general. Okay, that's not true. Second, the ratio of logs you might think is log base b minus log is the difference of the logs. Again, that's also false. Another one, this one is log to a power is not, you can't pull the power, it has to be log of x cubed. right? Log of x cubed, not log of x quantity cubed. Right? So don't do that.
These are all things you shouldn't do.
These are all false. These are all these things are false. Don't do them. It's not true. So these are examples of common errors. Examples of common errors. I'm going to put a big X just to make sure you understand these are not rules.
So number 4 is not true either.
None of these is true. Nor-
What's wrong with number 3? What's wrong with number 3?
Okay, so what we have over here is that log of something to a power, you can pull the power out. Okay, that's different from log of something to a power. It's not the same thing as log of something to that power.
So if it wasn't the whole quantity, it would be okay. Okay, gotcha.
Yeah, so that's the one I think that people are likely to make. The others are hopefully you will not make. I don't think 4 is likely. Why would anyone do that? Right? That's just doesn't work. Yeah, these are sort of misremembered. Anyway, just remember, log of product is the sum of logs. Log of something to the power is the power times the log. Okay. So let's finish up with some problems. Finish up with some problems. So it is using the properties of log. See what you can say about these things. Log base 10 of 70 minus log base 10 of 70. 2 to the log base 2 of 5 minus 3 to the log base 5 of cube root of 5. Log base b of e to the b. And let's do this one also. Log base 10 of 30 plus log base 10 of 2. Just for fun. So these are sort of like, if you see something this, you can be a little clever and then reduce it to something simple. Let's do this one together. What is this? So log base b of b to the b. What is it? It's b. It's b, right? Because you can pull b out, and you get log base b. Well, log base b of b is 1. It's b. Okay, I'll let you guys think about it for 1 minute, and here's see what you can think. You can figure out these remaining things. And then we'll talk. Okay. against minus. What do you?
Number one,
Yes.
it's log base 10 of 70 over 7, which is log base 10 of 10, which is 1.
Okay. This one. Right. 50 cents. This is log base.
And the second one, did you,
Yeah, sure, why not? There's only 2 minutes.
okay, second one, would be 5 minus log base 5 to the, well, it'd be, the 3's would cancel, so it'd be log base 5 and 5 would be 1, so it'd be 4.
Okay. So here you can put the 3 back. You put the 3 back in, right? So you get, right, put the 3 back into the exponent, right? The 3 and the root 3 cancel, right? And you get 5 minus fancy looking 1, which is 4.
And last one would just be log base 10 of 30 times 2, which is log base 10 of 60.
Is that it?
Yeah.
Is there anything else you can do with this? Log base 10 of 60. I guess you could do something like this, log base 10 of 6 times 10, right? Then I don't see that this makes it any better. It's good to do like the log of a product, use the sum of the logs. Okay, so it's 1 plus log base 10 of 6. Is that better? Right.
Oh, okay.
Right.
Is that what you're going
I don't know. I think maybe that's what. Go on.
How did we get 5 for, yeah, how did we get that 5?
Remember, 2 to the blah, 2 to the x, and log base 2 are inverse functions.
Oh,
So they cancel each other out, you get 5.
got it.
Okay, question.
Oh, no, I didn't see the 2 that, I think I said in the first video.
Okay, that's it for today.